We are now in 11.1, and we're talking about, this chapter's on power series, and the goal here is to approximate a function with a polynomial. So we're going to take an odd function like maybe the sine of x, and we're trying to come up with a polynomial that approximates it. And that is the end result here, what we're trying to do. So if you're doing a linear approximation, the interesting thing is it's just actually y minus y1 equals m times x minus x1. Or in our case, we are trying to get a linear approximation for some function, and we've got some strange function I don't have a name for, at the point A. And we're going to approximate it by a line. So we're trying to find a line that close to A, in this little neighborhood here, the line is approximately the same answer as if I actually plug the A into the complicated function. So all I have to do is get the equation of a line. Well, we know what's going on here. We're doing it at that point, so the point is A, f of A, and so this would end up being y minus f of A equals, the slope is our derivative at A, and then x minus A. And if we cleaned it up, we get f at A plus the derivative at A, x minus A. And that would be a linear approximation. If we're trying to do a polynomial, that takes a quadratic approximation, that takes a little more work. And since it's a linear approximation, it has a degree of 1, we are going to call this p sub 1 of x is equal to this equation. So if I'm trying to get p sub 2 of x, you're going to start out with p sub 1, the linear part, and then we need to add to it the quadratic term. So we're going to add to it another constant, and now it's going to be x minus a squared, because this part's the linear part, and this part right here makes it quadratic. Now, as this turns out, it ends up, and you can read this in your textbook, it ends up that p sub 2 is going to be f of a plus f prime at a, x minus a, plus, now it's going to be f double prime of a over 2 x minus a squared. And they've developed that in the book for us, so you can find it. So let's use this information for example 1. Find the linear approximation of f of x equals ln of x at x is 1. So what I need here is I need the derivative. Actually, I need both things. I need to figure out what this is at 1, and it's 0. And then I need to figure out the derivative, which is 1 over x, and plug in 1 for it, and it is 1. So, according to my formula, for part A, P1 of x is going to be equal to f at A, which we figured out to be 0, this guy right here, plus the slope, 1, I'm going to rewrite it. Zero plus the slope, which was 1, and then x minus 1. And if I clean that up, P1 of x is just x minus 1. That is a line. And in the book they have a picture drawn for you so you can see what's happening there. But it matches pretty closely. You have your natural log function, which goes like this. And then you're approximating at the point 1, which is right here, the line that is close to it, and then we're also going to get the parabola that is close to it. So the parabola, part B, quadratic, we now need a second derivative, which first derivative is x to the negative 1, so this is negative x to the negative 2, and when you plug in 1, you get negative 1. So now p sub 2 of x is going to be f at 1, which was 0, plus f prime at 1, which is 1, x minus 1, plus f double prime at 1, which was negative 1, over 2, and then x minus 1 squared. If I clean that up, I end up with x minus 1, and we're just going to leave it like this. It looks a little weird, but there's no sense to multiplying it all out. And then part C wants us to take those two answers and approximate the natural log of 1.05. So P1 of 1.05 would be equal to, P1, where did it go? X minus 1, so 1.05 minus 1.05. P2 of 1.05 is going to be that 1.05 minus 1, and then it's going to be minus a half 1.05 minus 1 squared. And when you put that in your calculator, you get 0.04875. Now, if you actually went to your calculator and did the natural log of 1.05, you get 0.04879. So what that's done for us is it's given us a way to get really close to the actual value for the natural log of 1.05. However, we never had to use the natural log button. So it makes it a little easier on very complicated questions. Now we're going to start talking about Taylor polynomials, and it's not going to fit on this page, so I'll do it in the next one.